Good afternoon, students. So, last class we discussed about why the overhead transmission is better than the underground, and also what are the overhead transmission line conductors, line supporters, and also types of insulator properties, types of insulators we discussed about the last class clearly. Now we go for the potential distribution over a suspension insulator string. That means how the voltage will be distributed in each and every insulator. A string of suspended insulators consists of a number of 4-cylinder discs connected in series through a metallic links. Look at the figure 1. So, 3 discs will be available. Total voltage across the disc is V, and voltage across disc 1 is V1, voltage across disc 2 is V2, voltage across disc 3 is V3. So, now each portion of 4-cylinder disc between 2 metallic conductors, 2 metallic links, each disc form one capacitor. This is known as mutual capacitor. Each disc will behave as a capacitor. So, that capacitor is also called as mutual capacitor or self capacitance. If there were a mutual capacitance alone, then the charging current would have been same through all the discs. Therefore, voltage across each unit is same, that is V by 3. In actual practice, capacitance existing between metal fitting of each disc and tower is known as shunt capacitance C1. Due to shunt capacitance, charging current is not same throughout the disc. Therefore, voltage across each disc is also different. Obviously, the disc nearest to the line conductor will have the maximum voltage, that is V3. Here we are consider 3 discs, that is why the disc nearest to the conductor is V3, will be much more than the V2 and V1. So, once again look at the figure. So, this is capacitor, each disc will be acting as a capacitor, and suppose it is ideal. So, total voltage is same, that is V by 3, V by 3, V by 3, but practically, so a leakage current will be there, that is this one C1 will be added. Whenever the C1 will be added, so because of leakage current, the voltage distribution will be different, V1, V2, V3, right. So, voltage impressed on a string of suspended insulators does not distribute itself uniformly, right, across the individual disc due to the presence of shunt capacitance. Because of shunt capacitance, voltage is not uniform throughout the disc, throughout the string. If it is a shunt capacitance is negligible, then voltage across throughout string is same. The disc nearest to the conductor have the maximum voltage, right. In our example V3, disc 3 is nearest to the conductor, that is why. So, V3 is maximum compared to the V1 and V2. The unit nearest to the conductor is under maximum electrical stress and is likely to be punctured. Therefore, so it must be provided to equalize the potential across the each unit. So, because of maximum voltage nearest to the conductor, there may be chances to breakdown is more. So, therefore, we have to provide equalized potential across each unit, then only we can reduce the electrical stress on nearest to the conductor. If the voltage impressed across the string were DC, then voltage across each unit would be same. Suppose if it is a DC, so voltage must be same. It is because of insulator capacitance are ineffective for DC. So, what is string efficiency? So, most important problem wise, this topic is very important. Sometimes they are asking derivation also. So, string efficiency is nothing but it is a ratio of voltage across the total string to the product of number of discs, and voltage across nearest to the conductor is known as string efficiency. String efficiency is voltage across string divided by number of discs n into voltage across nearest to the conductor, right. So, what is the main aim of this one is The unequal potential distribution is undesirable and is usually expressed in terms of string efficiency. By using string efficiency, we can decide the performance of insulator clearly. So now how to derive the mathematical expression or potential distribution over a suspension insulator. So as usual, we know about 3 discs will be there. So each disc will acting as a capacitor C, 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 and these are the shunt capacitance, that is C1, C1. Here I1 current is there, I2 current is there, I3 current is there. So voltage across nearer to the conductor is V3, V2, V1, total voltage is V, right. So here let us consider self capacitance of each disc is C. So these are the in line, each disc will acting as a self capacitances, but mutual capacitance is between line conductor and this one cross arm. Let further assume that shunt capacitance C1 is some fraction of K of self capacitance. This is most important. C1 is equal to Kc. C1 is equal to Kc. Starting from the cross arm or tower, the voltage across each unit is V1, V2, V3. From the cross arm, voltage across disc is V1, voltage across disc is V2, voltage across disc 3 is V3. Now applying Kirchhoff current law at node A. Suppose this is node A, you can consider node A, node B, node C. Applying KCL at node A, that is nothing but, so sum of the incoming currents is equal to the sum of the outgoing currents entering into node A. So here from node A, small I1 is leaving, capital I1 is leaving, but capital I2 is incoming. Therefore, incoming current I2 is equal to leaving currents small I1 plus capital I1. So I2 is equal to capital I1 plus small I1. We know that charging current. So already we discussed about the charging current in the second unit, performance of transmission lines, and we know the formula charging current V by XC. XC is nothing but 1 by omega C, that is 2 pi Fc, right. So V1 omega C, charging current is nothing but V1 omega C. So as usual, I2 is nothing but V2 omega C, I1 V1 omega C plus small I1 V1 omega naught C, it is C1, right. Charging current in shunt capacitance C1 is nothing but V1 omega C1. So V2 omega C, here V1 omega C and V1 omega. What about C1? C1 from the definition, C1 is equal to Kc. Here substitute Kc. Therefore, take a common factor of omega C. So we have to cancel to each other, omega C, then V2 equal to V1, taking a common factor V1 into 1 plus K, V2 is equal to V1 into 1 plus A. So consider as a equation 1. Similarly, applying KCL at node B. So incoming current is I3, capital I3, outgoing currents are capital I2 and small I2. Therefore, applying KCL at node B, capital I3 equal to small I2 plus capital I2 as usual. I3, that is nothing but V3 omega C, I2 V2 omega C plus what about small I2? Small I2 is nothing but, so voltage distribution, that is V1 plus V2, both have to consider. Leakage current because of these two discs, that's why. So I2 is equal, small I2 equal to V1 plus V2 omega C1. So V3 omega C, V2 omega C plus V1 plus V2 omega. What about C1? As from the definition, C1 is equal to Kc. Shunt capacitance is the K times of the self capacitance. So taken common factor as omega C, V3 is equal to, and cancel to each other both sides, V3 equal to V2 plus V1 plus V2 into K. So V1 K1 plus V2 1 plus K. So KV1 plus V1 into 1 plus K square, that is taken as V1 as common factor. So put V2 in place of V1 into 1 plus K, that is K into 1 plus K square. So V3 is equal to V1 into 1 plus 3K plus K square, taken as equation 2. V2 is V1 into 1 plus K, remember clearly. So equation 1, equation 2, equation 3 is, remember, always that may be helpful to competition exam also, gate exam also. So V2 is equal to V1 into 1 plus K, V3 is equal to V1 into 1 plus 3K plus K square. Then another one. So the voltage between the conductor and earth, that is V, capital V is equal to V1, total voltage V is equal to V1, sum of all individual voltages, that is V is equal to V1 plus V2 plus V3. We know V1 as usual, V1 plus V2 means V1 into 1 plus K plus V3 means V1 into 1 plus 3K plus K square. So combined that one, V1 is taken as common factor, V is equal to V1 into 3 plus 4K plus K square, taken as roots for that equation. We are getting V is equal to V1 into 1 plus K into 3 plus K. Now taken as equation 3. From expressions equation 1, 2, 3, from expressions equation 1, 2, 3, we can get, so V1 by 1, V2 by 1 plus K, V3 by 1 plus 3K plus K square, V by 1 plus K and 3 plus K. That means we have to getting the relations in any form. V2 is V1 into 1 plus K, but V1 is V2 by 1 plus K. V3 is 1 plus 3K plus K square into V1. Otherwise V3 in terms of V2. So whatever it may be, from this equation we can get every value. So now first of all find out the V1 individually. V1 voltage across topmost unit is, so V1 is equal to V by 1 plus K. So these 3, V1 is equal to V by 1 plus K, 3 plus K. This is the topmost unit voltage. Voltage across second unit, as usual V2 is equal to V1 into 1 plus K, and third unit V3 into V1 into 1 plus 3K plus K square, right. So therefore we determine the individual voltages from top of the tower to bottom of the tower or nearest to the conductor. Now total voltage also is known, V is equal to V1 plus V2 plus V3. Therefore determine the string efficiency. Now once again, what is the string efficiency? It is the ratio of voltage across the string to the product of number of discs and voltage across nearest to the conductor. So here voltage across string is nothing but V, N is nothing but number of discs is 3, and voltage across nearest to the conductor is V3. Therefore string efficiency for the above expression, above derivation, is V by 3 into V3 into multiplied by 100, that is nothing but percentage string efficiency. So from the mathematical analysis, so we can observe the following points. Suppose if K equal to 0.2, let us consider, from expression 4 we get V2 is 1.2 V1, V3 is 1.61 V1. This is clearly give you an idea about the disc nearest to the conductor is maximum voltage. V3 is nothing but 1.64, but V2 is 1.21, V1 is 1, V1 is 1, V2 is 1.2 and V3 is 1.64. That is nothing but, so clearly known about the disc nearest to the conductor is maximum value or maximum voltage across it. The voltage across the other disc decreasing progressively as the cross arm approaches. That means V3 is greater than, V2 is greater than V1. The greater the value, K is equal to C1 by C, and more non-uniform potential across the disc and lesser the string efficiency. Now another most important for B.Tech point of view, the methods to improve the string efficiency. Generally just now discuss about the potential distribution across the string of suspension insulators, that is not a uniform. So V1 for first voltage across first disc is V1, voltage across second disc is V2, voltage across third disc is V3. So that V1, V2, V3 are not equal to each other. That means, so potential distribution in a string of suspension insulators is not uniform. The maximum voltage appears across the insulator nearest to the line conductor and decreases progressively as cross arm approaches, right. If the insulation is highest stressed insulator, that is the nearest to the conductor, So that may be breakdown because of flashover takes place. Why? Because most highest voltage appear across the V3 only. That means if flashover occurs, the nearest to the conductor disk will be breakdown. That may be other units will take place succession. So that means this is the necessity to equalize the potential across various units of a string of suspension insulators. So that means to improve the string efficiency, that may equalize the voltage across the all disks. So basic methods to improve the string efficiency is very important. First one, by using longer cross arms, that is nothing but K value is high. K value is high. K is equal to C1 by C, right? So next, by grading the insulators by using guard ring. So look at the first method, by using longer cross arms. So this is the tower, this is the cross arm. We have taken longer cross arm, that means shunt capacity is high. So the value of string efficiency depends upon the value of K, the ratio of shunt capacitance to mutual capacitance. Lesser the K value, greater is the string efficiency, and more uniform is the voltage distribution. When K value is lesser, so string efficiency is more, and also uniform distribution, voltage distribution is also occurred. The value of K is decreased by reducing the shunt capacitance. So reducing this one, so we can improve the efficiency. In order to reduce the shunt capacitance, the distance of conductor from the tower must be increased, that is longer cross arms are used. However, the limitations of cost and strength of towers do not allow the use of very longer cross arms. In general, the practical value of K is 0.1, that can be achieved by this method. Next one, by grading the insulators. In this method, insulators of different dimensions are so chosen that each has different capacitance. Insulators are capacitance graded, that means they are assembled in the string in such a way that the top unit has the minimum capacitance and increasing progressively as the bottom unit, that means nearest to the conductor is high value. Since voltage is inversely proportional to the capacitance, this method tends to equalize the potential distribution across the units in a string. The main disadvantage of this method is large number of different insulators are used, that is nothing but large number of different sized insulators are used. However, good results can be obtained by using standard insulators for most of the string and larger units, for that nearer to the line conductor. Look at the figure, these are the guard rings. So we can use extra point. Look at the guard ring like this. The potential across each unit in a string can be equalized by using guard ring, which is a metal ring electrically connected to the conductor and surrounding the bottom of the insulator as shown in figure. The guard ring introduces the capacitance between the metal fittings and line conductor. Now the guard ring is connected in such a way that the shunt capacitance current I1, small I2 are equal to metal fitting line capacitance I1 dash and I2 dash. So this is I1, this is I1 dash, this is I2, this is I2 dash. Both are cancelled to each other. Consequently, there will be uniformly potential distribution across the unit. That means there is no shunt capacitance, means we are getting uniform distribution. So next, causes of insulation failure. Insulators have to withstand both mechanical and electrical stresses. Mainly electrical stresses are due to the short circuits and also line voltages that may cause breakdown of the insulator. If breakdown of insulator may occur because of flashover or puncture voltages. In flashover, the arc occurs between the line conductor and insulator pin So flash will occur insulator pin and line conductors. Insulator pin is nothing but earth, and discharge jumps across the air gap following short distances. Figure shows the arc distance, that is A plus B plus C. So this is this one, figure 8.6, A plus B plus C for the insulator. In case of flashover, insulator will continue to act in its proper capacity unless extreme heat produced by the arc may destroy the insulator. In case of puncture voltage, the discharge occurs from the conductor to pin through the body. When such a breakdown is involved, the insulator is permanently destroyed due to excessive heat. In practice, sufficient thickness of porcelain is provided in the insulator to avoid puncture by line voltages. The ratio of puncture voltage to flashover voltage is known as safety factor. At the starting, I will give you a clarification. The ratio of puncture voltage to flashover voltage is greater than the 5. So that is the safety factor is the ratio of puncture voltage to flashover voltage. While solving the problems relating to string efficiency, so first of all, we have to, the following points may be noted. Maximum voltage appears across the disc nearest to the conductor. Voltage across the string is equal to phase voltage. Voltage across string is nothing but phase voltage, not a line voltage. Voltage across the string is equal to voltage between line and earth, that is phase voltages. Suppose we are getting the line voltage √3 into voltage rating of the string. So in this manner, we have to calculate the string efficiency as high as possible. That means by using longer cross arms, and also by using guard ring, and also by using grading of cables. These three methods are very, very important for improving the string efficiency. Thank you. So next class we discuss about the corona, concept of corona, why corona occurs in the transmission line, and what are the causes of occurring corona losses, and what are the different parameters involved in the corona loss, and what is the empirical formula for corona loss, and what are the factors affecting the corona loss, what are the methods to reduce the corona loss. All these things will be discussed in the next class. Thank you. The problems involved by using string efficiency is also important. That means the problems will be explained in later classes. So mainly in this insulators, so they are asking question like this: explain the types of insulators, question number 1. Question number 2, explain the voltage distribution across suspension type insulators, that is the derivation of string efficiency. That is, voltage potential distribution or voltage distribution is nothing but V2 is equal to V1 into 1 plus K, V3 is equal to V1 into 1 plus 3K plus K square. So like that we have to derive it. And string efficiency also, string efficiency for 3 disc insulators is V by N into V3 into V3. So we are doing some problems in the next classes. First we will completely discuss about the theory of third unit, then we discuss about the problems on insulators, problems on corona, problems on sag, right. So third unit having 3 subtopics: insulators, corona, concept of corona, and mechanical, I mean sag. So first topic is completed for this class. So next we go to discuss the corona concept, right. Thank you one and all.